So by utilizing our criteria for phase separation, we're able to develop an equation that tells us, or that will allow us to predict when phase separation occurs. But in the form that I have now, this is a general form, and so it's a bit abstract. And so to make this a little bit more instructive about, how useful this equation is, what we need to do is we need to actually plug in an equation for the excess Gibbs energy. Plugging in model for G excess. Okay. And so let's start out with the simplest model we could think of, which is that one parameter Margulies equation. Okay. So where we have and we're going to be multiplying it since we have an RT here. Let's multiply it by RT. 1 x2 a x1 1 minus x1 a. And so if we take the first derivative of this, I'm going to pull out the a, which is not a constant. This is, remember, this is a function of temperature. So ART, we get 1 minus x1 minus x1, which gives us ART 1 minus 2x1. And then if we take the second derivative, we get minus 2 ART. Okay? And so what we'll do now is plug in this result into here. And so we'll have, or actually not into this equation, we're going to plug it into this one, the inequality. So we have 1 RT x1 x1 1 minus x1 minus 2a RT. The RT's cancel. This is less than 0. And so what we get, if we rearrange this equation, is that our Margulies parameter for the one parameter Margulies equation, when that a value is greater than 2x1 1 minus x1, that's when we have phase separation. Okay. So criterion for phase separation if one parameter Margulies is used. Okay? Alright, and so I'll say A has to be greater than or equal to 2. Or in fact, actually, let me rewrite that so it's less confusing. In fact, if you play around with this equation, and you even just try calculating, when this equation would work. This equation, since we know that x1 has to be between 0 and 1, so this equation is only true if your a value is greater than or equal to 2. Okay? And so to illustrate this, or just to emphasize why this relation is useful, remember that in the one parameter Margulies equation, our a is actually a naught over RT. And if you know your a value, you could solve the equation to get x1 alpha and x1 beta. Because we see here that we have two roots on the bottom, and so you should be able to get two x1 values out of it. And the lower one and the higher one are going to correspond to different phases. All right, and so to kind of give you at least some, understanding of how this equation works, let's go through some examples where you plug in numbers. And so, for example, let's say our A is equal to 5, and so we're at some temperature and we have some A0 value where this ratio gives you 5. We know 5 is greater than 2. And so then if you solve the equation, you would get your lower value, which I'll call alpha, is 0.113, and your higher value, which I'll assign to beta, is going to be 0.887. Okay? If you decrease A so that it's 4, then your x1 alpha is 0.21, and your x1 beta is I looked at the wrong number. Your x1 alpha is 0.146, and x1 beta is 0.853. Decrease A to 3. x1 alpha here is 0.21, and x1 beta is 0.79. And if you go all the way down to a value of 2, what you see is that you'll only get one root. So x1 alpha is going to be equal to x1 beta, and it's just going to be equal to 0.5. Okay? And so if you kind of look at these numbers here, you can kind of see a trend that as we decrease A, the distance between x1 alpha and x1 beta gets smaller and smaller until we get to that critical A value of 2, where the x1 beta and the x1 alpha values are equal to one another. So distance between x1 alpha and x1 beta increases as A increases. Okay? All right, and so the thing to remember is that A parameter is a function of temperature. Right? And so based on this equation, you could also kind of rewrite it or use it to actually calculate that Tx1 diagram that we've been kind of looking at this entire time. Okay. All right, and so I'm going to go to the next page and kind of sketch at least what this equation is telling us mathematically. So for instance, for A, if we plot A on the y-axis and x1 on the x-axis, right, what we would see is that when we're above a value of 2, we would get a curve like this, where this left side corresponds to x1 alpha, and this right side corresponds to the x1 beta values. And so if we're at really high A, that distance between the two values, or in other words, or another name we call it is the miscibility gap. That miscibility gap is very big. But as we decrease A towards the value of 2, that distance between the two decreases until they merge to the same value. Okay? And for the one parameter Margulies, that value is 0.5. Okay? If we drew this, we could express the same information on a Txy diagram, and it might be a little bit more intuitive at this point. So essentially, since A is just inverse to T, the TX diagram is just going to be the upside down version of this. Okay? And so here, once again, the left-hand side is x1 alpha, right-hand side corresponds to x1 beta. And the temperature here, which is that temperature that gives you a value of 2, we would call this temperature the critical temperature. Okay? All right, and so that's visually, we derived a mathematical equation that tells us when phase separation is going to occur. And we can use that equation to develop diagrams that look like this. The last thing I want to say is that, we found that at an A value of 2, we got a mole fraction of 0.5. And so that would tell us that that this is the sort of kind of critical mole fraction. But I want to emphasize that that's not a general result. And the other thing I'll also emphasize is that you could see that x1 alpha and x1 beta here, if you sum them up at all these A values, they sum to a value of 1. All right, but that's also not a general thing. In fact, the only reason we see that is because of what we assumed for our excess Gibbs model. And so you only see this, the reason we're seeing this is because we're using a single parameter Margulies equation. All right. And if you use some other model, so like the 2-parameter model or the Van Laar model, you probably won't see that. So I just want to emphasize that just so that you don't get the wrong idea that x1 alpha and x1 beta have to equal 1. That's only true for the single parameter Margulies.